If you've spent any amount of time exercising outside in the summer, you've likely experienced dehydration to some extent. In physiological terms, dehydration occurs when you have a loss of water in your body. Water has a huge role in our body. It acts as a solvent. It also is involved in many chemical reactions in our body as well. So we have a variety of problems that occur in our body when our water levels become very low. Now, in organic chemistry, dehydration actually refers to a specific reaction that occurs when we are low on water. So this reaction is actually going to break water out of an alcohol and release it as one of the products. So it actually creates more water as you are low on water. A dehydration reaction occurs when we have an alcohol, such as the example alcohol shown here, reacting in the presence of a strong acid, such as sulfuric acid, although we also see things like phosphoric acid used here as well. And we generally do this reaction in the presence of some heat. Now, what happens in our reaction, so when we have a strong acid with an alcohol, that alcohol is going to get protonated. We've seen this, of course, before with our SN1 nucleophilic substitution reactions. So our strong acid is going to act as the source of hydronium ions. So of course, remember that in an aqueous solution, a strong acid will always protonate water in order to form our hydronium ions. So we can show that here in our reaction. Now we're going to use our strong acid to protonate our alcohol. So this is a protonation step. And as usual, our product here of this initial step is going to be our alkyl oxonium ion. Now, of course, as our hydronium ion is reacting as the acid, we're also going to be producing water as our conjugate base here. And of course, at this point, we've done exactly what we would do when we're doing a SN1 nucleophilic substitution reaction. So I want you to recognize the similarity here between that SN1 reaction and the dehydration reaction that we're showing here. Our next step, we're going to take our alkyl oxonium ion and we're going to break off our H2O, our water, that's acting as our leaving group. This, of course, would be our dissociation step. And after we break off that leaving group, we're going to form a carbocation. So again, you should note the similarities between this reaction and our SN1 reaction. We've disassociated and we've formed a carbocation. Now, if we're going to perform a SN1 reaction, our next step would be to attack with a nucleophile. However, in this case, we're going to do something a little bit different. We're going to do what we call a beta elimination. So remember that the alpha site is our reactive site, and then we can move with Greek letters to the beta site, which is our site adjacent to that reactive site. So by beta elimination, what that refers to is we're going to actually eliminate this hydrogen on our adjacent carbon, and we're going to use the electrons from this bond in order to satisfy the electron deficiency of our carbocation. So we're going to take our water here, and water, of course, can act as a weak base. So we can take our extra electrons on our oxygen, and we can come over here and grab that hydrogen. Now, at the same time, we'll take our electrons here from this bond and dump them in here to make a double bond. So we're going to make a double bond, so this carbon will now have 8 electrons, will no longer be a carbocation. This carbon will still have 8 electrons, right? It's not losing an electron, it's just losing that hydrogen. So at this point, we get our product, which will be an alkene. So we created that double bond as we eliminated our hydrogen here. So this third step is our beta elimination, or we could also refer to it as a deprotonation in the sense that we're removing our proton, our hydrogen ion, from our carbocation intermediate. So as we note here, our dehydration reaction takes us from that alcohol to an alkene. And it shares a lot of similarities to our SN1 reaction. The key difference is just our beta elimination step here instead of the association step that we would have with our typical nucleophilic substitution reaction. Now, you might notice here with this beta elimination step, I'm showing us removing a hydrogen over here on this carbon, but we also have lots of other hydrogens here that could potentially be eliminated instead. Right? We have a hydrogen over here, but we actually have 3 hydrogens, but these are all identical, so we only really need to consider one of them. We would have 3 more up here, and of course we also have hydrogens over here at the other end of the molecule, in addition to the hydrogen that I showed there. Now, of course, these hydrogens are not going to react because they're not beta hydrogens, and if we have hydrogens over here, we can't easily take these electrons and bring them over to the carbocation. There's just too much space in between these 2 carbons. We really only move our electrons from a bond to the adjacent atoms or bonds. So this doesn't occur because it's too far away, but we could still potentially react at this other set of hydrogens. So I'm going to show another water molecule and draw our other potential reaction route of beta elimination over here, right? So we could pull off this hydrogen, donate our electrons in there to form a double bond, and now we would produce an alternate product that would look like this. So, why did I draw this product initially? What's the difference between these 2 products? In both cases, I'm eliminating what I refer to as my beta hydrogen, right? That hydrogen on my carbon adjacent to my reactive carbocation site. Both cases, I'm bringing electrons in order to eliminate that carbocation, and I'm still producing that alkene. Well, the difference here is that if we look at our alkenes, you should notice that they have different substitution patterns. Now remember, in our last video we talked about how carbons that are attached to our alkene, that carbon-carbon double bond, can actually help to stabilize that alkene by donating some electron density through hyperconjugation. So in this case we have 1, 2, 3 carbons that are attached to our 2 carbons in that double bond. So we refer to this as tri-substituted. Up here we have only 2 other carbons that are directly attached to my carbon-carbon double bond. So this is di-substituted. Now that tri-substituted is going to be more stable than my di-substituted alkene, and we want to form the most stable product in our reaction. Right? We always want to go from unstable things to the most stable things that we can potentially make. So this alkene here will be the major product of this reaction. We could see some of this alkene forming, but it's going to be a more minor product. Right? There'll be small amounts of this because it's less stable, and larger amounts of this. So we can say this is our major product, and this would be a minor side product. So it's an important thing to note is that in a lot of our reactions, we're often not going to have just one product that will form. We'll usually have one major product, and then there might be some minor side products that form as well. We saw this as well with our carbocation rearrangements, right? So remember, if we have a secondary carbocation, that can potentially rearrange to form a tertiary carbocation that's more stable, and it can lead to a different product than we might otherwise expect. Since we have a carbocation intermediate here, we do have the potential for rearrangements, but note, of course, this is a tertiary carbocation since we have 3 carbons attached to it. So this is already our most stable carbocation, and it's not going to do any rearrangements. Now, this rule right here that we use to indicate that this is more stable and that's less stable, this is more likely to form, that's less likely to form, this is called Zaitsev's rule. So Zaitsev's rule says that in our elimination dehydration reaction, so note we call this an elimination reaction because we're eliminating that hydrogen, we're always going to produce the more substituted alkene. So we prefer that more substituted and more stable alkene. We're less likely to get that less stable and less substituted alkene. Now we can also tell something about the rate of our reaction based off of our reaction mechanism and of course the starting structure of our reactant. So remember, our carbocations are going to be most stable if they're tertiary, and they're less stable if they're secondary, primary, or methyl carbocations. Now we should note, of course, that if we start with a secondary alcohol or a primary alcohol, that will lead to a secondary carbocation for a secondary alcohol or a primary carbocation for our primary alcohol. It's the structure of our initial alcohol that will determine the structure of our intermediate, and the stability of that intermediate determines our overall reactivity. So our reaction is going to be fastest for a tertiary alcohol, and therefore tertiary carbocation, then secondary, and then primary. Of course, again, you should note that the final product that I drew is the most substituted product that we could get from this intermediate. Again, following our Zaitsev's rule. We do have a couple of possible minor products. So we could produce the monosubstituted alkene shown here if we took a hydrogen off of this carbon. We could also produce the diastereomer of this major product, which would be the cis diastereomer. This diastereomer, though, remember that cis diastereomers are less stable than trans diastereomers because we have the steric crowding between our carbons, and so this less stable product would be less likely to form. The dehydration reaction that we've looked at here is an example of an E1 reaction. So this terminology is similar to the SN1 terminology that we've used before. So that E refers to elimination. Right? We're eliminating hydrogens in order to form that double bond. The 1 refers to the fact that our rate limiting step, right here where we form our carbocation, just involves one molecule, right? So we have our single alkyloxonium ion breaking off to form that carbocation. As always, of course, that rate limiting step is the step where we form our carbocation because that carbocation is very unstable. Similar to what we've seen previously with our substitution reactions, our elimination reaction can occur with alcohols or with alkyl halides. If we have an alkyl halide, we're going to be eliminating our halogen as well as an adjacent hydrogen. And so we call this a dehydrohalogenation. We're going to move a hydrogen, remove our halogen, and we're going to end up making an alkene. Now, as usual, of course, we remove our hydrogen such that we create that more substituted alkene. Right? We're still following Zaitsev's rule here, just as we did with our alcohol before. but our mechanism is going to look a little bit different. So with our alkyl halide, we don't need a strong acid in order to protonate our halogen and make a good leaving group. Right? This halogen is already a good leaving group. Right? So it's ready to break off right now. It doesn't have to get protonated first. So since we have a good leaving group and we don't need acid, we can actually add base here to help to deprotonate and remove our hydrogen. Right? Before we had to use the weak base of water because we couldn't have any bases in a solution that's strongly acidic. We can't have any strong bases anyways. It'd get neutralized by that acid. In this case, we don't have to have the acid, so we're going to add a very strong base. The base I'm showing here is what we call an alkoxide. It's a negatively charged oxygen anion that has a carbon and alkyl chain attached. So this is F oxide since it's the 2-carbon alkoxide. We would usually have some cation associated with that as well, such as sodium or potassium. This would just be ionically interacting to counterbalance the negative charge of our oxygen. So this strong base alkoxide is going to be very happy to pull off a hydrogen. Right? It has a lot of electrons, it's a very strong base, it really wants that proton, and so it can actually come in and grab our hydrogen here at the same time that our bromine is popping off as a leaving group. So we have our bromine over here acting as a leaving group. This is acting as a strong base in this case. And of course, we just need our arrow here showing the movement of the electrons from our carbon-hydrogen bond over to our carbon-carbon bond to replace the lost electrons here from our bromine. So this reaction is actually occurring in one step, and of course we get a sodium bromide ionic compound as a side product as well. So since this occurs in one step that involves 2 reactants, we refer to this as an E2 mechanism. Again, it's very similar to the SN2 mechanism that we looked at before, but in this case we're eliminating instead of attacking our nucleophilic or electrophilic site by that nucleophile as it's breaking off. So it's a similar mechanism, but slightly different in where we attack as we go to form our alkene product. Now, of course, as usual, we can use the mechanism and the structure to learn something about the relative rate of our reaction. Now, since we only have one key step here, all of our components are going to be critical for determining our reaction rate. So we need to break this bond, and we also need to attack with our base, and both of these are going to influence our rate. So if it's easier to break our bond, if we have a better leaving group, we would say, then our reaction is going to occur more quickly. In terms of halogens, our leaving group is based on the size of the halogen. So our iodine is the best leaving group, and that's because it's lower down the periodic table, it's very large, which means it has a weaker bond to our carbon compared to our other halogens. Right? It's the same reason why our hydrogen iodide is a very strong acid. Right? Because it can very easily break that bond to the hydrogen and donate that hydrogen as an acid. So in terms of our leaving groups, our iodine is going to be the best, and our bromine will be second as the next largest, chlorine, and then fluorine. Out of our 4 common halogens, it's ranked from lowest on the periodic table to highest on the periodic table. And since our leaving group is involved in our key step here, this will influence the overall rate of our reaction. Now, the second thing that's going to influence our reaction rate is actually based on our alkene structure. So we don't have a carbocation intermediate, so we don't have to worry about whether it's a tertiary or primary or secondary carbocation, but the substitution does affect our final alkene product, which can also affect our reaction rate. So more substitute alkene is more stable, and so if it's more stable, it will have a lower energy and our overall reaction will be able to proceed faster. So we can say that tertiary is going to be faster than secondary, which is going to be faster than primary. And in this case, that difference in rate is just based on the substitution pattern that results from a tertiary versus secondary versus a primary alkyl halide. Right? So in this case, we had a secondary alkyl halide, and that led to our di-substituted alkene. If we had our bromine over here, the best alkene that we could get would be monosubstituted, and so our reaction would occur more slowly since we're going to a less stable product. Now, one of the things that you can note here is that this trend is actually the opposite of the trend that we saw for our similar SN2 reaction. And the reason for this is that in our SN2 reaction, right, we were mainly concerned about crowding. So our primary reactant was the least crowded, and so it would actually react the most quickly. In this case, our base isn't even reacting at that, what we consider our reactive site where we have our electrophilic carbon. It's just pulling off a hydrogen at a nearby carbon. So it actually doesn't even really care about the crowding. Right? Our crowding doesn't really matter. Since we're not actually attacking in where we have our leaving group and all that potential crowding, we don't really have to worry about how crowded our reaction is. So crowding is going to be important for our E2 reactions. Now, the last thing that I want to look at here with our E2 reaction is how the orientation of our molecule can influence the reaction. Now, as we're looking at the reaction here, so we can see, of course, we have our hydrogen down here that's getting pulled off at the same time as our bromine up here is breaking away. Now, we can, of course, represent this using our hybrid orbitals. So we have our bromine bonding to our carbon. Remember, this is going to be sp3, so we have our little lobe at the end from that small p characteristic. We have another bond coming out down here to our other carbon, which has a bond to our hydrogen down here. And again, I'm going to show my little lobe here. And the reason why I'm showing these, so as we are reacting here, so this bond is slowly going to be breaking. So we're slowly breaking off this hydrogen, and we're slowly breaking off this bromine at the same time. And as we're breaking that, we want our orbitals here to be ready to turn into p orbitals and line up perfectly to form our alkene. Right? So when we form our alkene, we're going to have those p orbitals and our carbons bound together, and we want our p orbitals to be perfectly lined up so that we can form that overlap and our pi bond. So what we actually need here is we need our bonds to be exactly anti with respect to each other. Remember, anti just means that there's a 180-degree angle between them. Because if they're anti, they're already in position so that they actually already are set up so that they can overlap in that side-to-side fashion as we go to make our pi bond. Right, so this is ready to immediately transition into our molecule over here. So our E2 reaction requires an anti-orientation. If we have a molecule that can't easily be rearranged into that anti-conformation, it will actually slow down or even prevent this E2 reaction. Let's take a closer look at this using Newman projections. Remember, our Newman projection is representing us looking directly along a bond. Right? So in this case, we're looking at the bond from our second carbon that has the bromine over to our third carbon. So the third carbon is in the back. It's hidden because we're looking straight down the bond. We have our bond going out to the other two carbons over here on the right. The bond out to the first carbon, right here attached to the carbon that has our bromine. And of course, we have our hydrogens here as well. So currently, we are 180 degrees relative to our anti-hydrogen. Right, so this is where we're set up, where our orbitals, if I added those in, would be perfectly aligned and set up to make that new pi bond. Now let's take this and rotate it 60 degrees, so we get to, so we're anti between our bromine and our carbons. So this actually might be one of our more stable conformations because we're taking our large group and putting it further away from our large bromine. Now, of course, we also have our carbon over here that's going to be clashing with that as well, so it might not actually be more stable. But it is another possible orientation of our different conformations. So we're going to have our bromine on top, our carbon over here, hydrogen over there. We're going to use our circle to represent our bond going back to the carbon behind us. And now we have our two carbons at the bottom, and our hydrogens coming out to the side. Okay, so at this point, right, we would have our bond here. Right, there's our sp3 orbital going out to our bromine, and we'd have our sp3 orbital over here going to our hydrogen. Right, this is going to be our hydrogen that will eliminate as we're trying to form our double bond. Now remember, in order to form a pi bond, our p orbitals have to be perfectly lined up. They have to be parallel to each other. In this case, we're going to break this off and form our p orbital. Right, so I'm drawing it dotted because it's happening behind our carbon bond here. So there's our p orbital that forms after the hydrogen breaks off. When our bromine breaks off, we get a p orbital right here. Our p orbitals are twisted relative to each other, and they actually can't form a pi bond until we rotate our bond here. Right? So it actually prevents our bond from forming as easily when that hydrogen is an anti. So we actually have to rotate it around so that we have our new p orbitals that are forming perfectly lined up in order to form that new pi bond. As we'll see, this can have some consequences in that if we have any molecules that can't easily rearrange into this anti-conformation, it again can prevent that E2 reaction. So our elimination reactions that we've looked at here are great ways to make alkenes. They also represent a new reaction that we can have with our alcohols and our alkyl halides. So before, of course, we took a close look at our substitution reactions, but now we see that we also have this elimination reaction. Now what you might notice here is that the reaction conditions that we've used are actually very similar to the reaction conditions that we've used for substitution reactions. So in our next video, we need to take a closer look at how we differentiate between substitution versus elimination reactions. When are we going to have a substitution versus when are we going to eliminate to form our alkenes?